I would like to introduce this discussion session about measuring quantum gravity in the lab. Our conductor is Sougato Bose from Oxford University. No, not anymore. University College London.
Yeah,
Sorry about that. Thank you. Please don't hesitate to raise your hand and be part of the conversation. I just want to say, if you need to write the questions, to write drawings, you can ask for using the virtual whiteboard. And well, I know there were already a lot of questions from the lightning talks, so bring up your questions, and I leave the lead to Sougato.
Okay, thank you. And the lightning talks have been very interesting, and also. I see a lot of friends here whom I'm yet to say hello to, but I will say soon, yeah. I think, so I have made a few points to discuss from when I was hearing the talks, but I thought maybe it's not a bad idea to start from, if you have specific questions to the talks of, the 4 talks that were presented, then maybe we start with those and then we go to, further discussions. Right. So does anyone want to start with a question on one of the other talks? Right. So maybe to start off, I will start off with it's a question kind of. So maybe a general. We start from a very general direction, right? So there are these explanations, whether this experiment that when you entangle 2 masses or even generate Nongaussianity. So there are these debates whether that really proves the quantum nature of gravity. Of course, I'm firmly on the side that it does. Okay, and as Marius showed, our reasoning towards it. But that, of course, assumes locality of interactions. But of course, locality not. So these days, I also modify the definition of locality. It's less to do with real, spatially local, but to do with the fact that one object interacts with another through the mediator. But there are these other developments. How many people think that it is settled that if 2 masses are entangled, then the gravity must be quantum? Okay, so very few consider it settled. Okay, so the question. So now I would like to raise is that say including up to the latest work that Marius has showed, which considers the time causality of the things. And there's this work also by, started by the Vienna group, but also by Bob Weld and others on relating the real and virtual gravitons, or the Newtonian field and on-shell gravitons, and also our stance that it is you need these virtual gravitons with the assumption of an interaction. So any comments that what else needs to be done here for it to be convincing? Yeah, Carlo.
Just to break the ice and start, I would say the following, and I would like to know if people disagree with that. If I'll probably slightly oversay it, so maybe I will have to backtrack. If the experiment is done, let's go with this, and the entanglement is measured, okay, and somehow the experimenter convincingly tell us, okay, this was not an electromagnetic thing, or something else. So it's, then I see, okay, I put this way, I see only 2 possibilities. Either special relativity is wrong, there really are instantaneous interaction at distance, or the gravitational field can be in a quantum superposition, meaning it can, to be quantum superposition means to give rise to interference. It doesn't mean anything else. But that meaning the gravitational field is a quantum position. Therefore, space-time geometry can be in quantum superposition, and therefore, space-time geometry, it's just not classical in the sense of being. So I repeat, either we have an argument for space-time geometry being in quantum superposition, or we're completely wrong about special relativity, field theory, and there are action at distance, which will be even more spectacularly changing everything we know about reality.
Right.
So I don't see any other way in which one could make sense of a positive result of the experiment, and therefore, from this perspective, the experiment is infinitely meaningful for our understanding of quantum gravity special relativity. That's what I would say. Is that
okay? Okay,
yeah.
Thanks,
That's
Carlos.
a extreme position. Yeah.
Yeah, yeah. Any other comments in this direction? Yes, yes.
Yes, this is a comment in the same direction. I would like to hear the opinion, especially of the igniters of this discussion.
Right.
And it's in the same line. If the experiment is done and entanglement is measured, then the thing I would like to hear what the positions and the opinion are first, do you expect that elementary quantum mechanics with a standard Newtonian potential actually gives the prediction and matches the results of the experiment? It's, to me, the easy question that I just want to make sure that like we agree on one point. And then the second point is we often consider this thing is called semi-classical quantum gravity, especially in like models where the black hole evaporates slowly. That is classical G mu nu equal expectation value of T mu nu. So do you expect that this semi-classical quantum gravity is incompatible with what is going to be measured, in the sense that this is an approximation of full quantum gravity, and it's a bad approximation for these experiments. And so in this sense, we are going to learn something that goes beyond semi-classical quantum gravity, which many are convinced that is something that we need to do to understand black hole evaporation at late times. And then I have many more questions, and some of these have to do with the relation to cosmological perturbation theory, where some similar questions arise. But I would like just to stop and see if there are comments on these first two. So elementary quantum mechanics and semi-classical quantum gravity.
Yeah, Mario. Mario, there is a mic for you.
Yeah. Okay, but to just state these questions, so it's predicted by quantum mechanics with a Newtonian potential, clearly. The general expectation, maybe you have more subtle ideas, is that it will rule out semi-classical gravity. Now, having said these two things, okay, let me make a couple of comments. So first of all, I disagree a bit with Carlos. I think I understand the position of somebody saying, guys, this is a thing that's operating in the Newtonian regime. You can say as much blah, blah as you want. I don't see important quantum gravity. I think that's fine, right? And I don't think this is going to be resolved. I mean, if you do the experiment, people can have this position for another 100 years. The interest of the experiment does not lie on disproving semi-classical gravity either, because there is a protocol to do that. And let me quote Bill Unruh that we had a discussion and he put it nicely. He was saying, it's related to what Eugenia said. He said, guys, if we do not see this effect, what I would be worried about is quantum mechanics, right? So how is this related to quantum gravity to begin with? And another comment he had is that I was sort of giving a speech that, look, it's so difficult to do quantum gravity experiments. This is something above nothing, that we're not saying it's too much, but it's something. And he said, yeah, okay, but the question is how much above nothing is And this is sort of the discussion. Personally, I'm really pushing this point. What I find interesting is the opportunity it presents to understand how quantum field theory works in a physical regime that previously there wasn't really motivation to do that. And I find very intriguing that many people are trying to figure out exactly what are these excitations, how do we describe them, and is not yet sorted. I think it's interesting to think what exactly is going on, irrespectively of the, if you want, epistemological discussion of should we be taking it as important or not. There is an independent interest on understanding this physical regime.
Okay, yeah, Kaslav has some comments. Maybe, yeah, you can take the Kaslav.
Hi. So it seems to me that we are at the moment of discussion which is comparable with the one maybe 15 years ago, or maybe even more, about whether the experiments with atomic fountains really are proof of general relativity or the general relativistic effect on quantum systems. And what they do, people there, is just in the gravitational field of Earth, they put a particle in a superposition of different heights. And if this is a part of the interferometer, at the end you see a gravitational-induced phase shift. And then there was a kind of a dialogue between Stephen Chu and collaborators, Holger Müller as an experimentalist on one side, and the Cohen Tanucci on the other side. And the first group claimed that the gravitational phase shift is due to general relativity, and the other group claimed, well, it can't be, because we can think about that just as in Newtonian gravity. You have a particle, quantum particle in Newtonian potential. So there is no reason that we should introduce time dilation or whatsoever, what the first group introduced. Now, the thing is that, of course, you can use a stronger theory to describe this effect, but there is no need. If you can describe this with a lower level theory, then the experiment, the phenomena cannot be a proof of general relativistic effect. Now, it seems to me that now, when we are talking that this experiment shows superposition of space-times, maybe we are a little overdoing it. At the end, I believe this is true, but maybe the fact that we just see where we have two particles interacting with each other and seeing the phase shift, that there is an alternative explanation of that, and that's that there is some kind of Newtonian interaction. Maybe this Newtonian interaction is also with a finite speed of light, but nevertheless, it's a Newtonian interaction. Now, in order to prove, and this will be a very important step, but in order to go beyond and claim that this is a superpositional space-times, we need to do exactly the point that we have done when we got convinced that GR is a geometry. Namely, to take many different, for example, clocks, and seeing always the same time dilation. That doesn't depend on how the clocks function or internal structure of the clock or whatsoever. Then we started to think it's not about the clocks, it's about the space-time. In here, the equivalent experiment would be harder, unfortunately, namely, not to have two structural particles gravitationally interacting, but having at least one of them being a clock, a quantum clock. And then seeing that depending on the position of the one and the other particle, we have really superposition of the times as shown by the clock. And we will see that this doesn't depend on internal structure of the clock. And then that will be, I think, the proof that we can conclude it's really superpositional space-times. And I have little doubts that this will happen, but that, I think, is an important step to be done.
Okay, thank you. Maybe Carlo wants to continue a little bit. Yeah, thanks. Yeah, it's coming that way.
Yeah, I have two comments. First, I want to answer Eugenia, two questions, and then comment what Czeslaw said. So Eugenia, two questions was, is the experiment, can the experiment be described by the relativistic quantum mechanics? And would it give the theory would give a description of what we see if we see the entanglement? The answer seems clear, this is yes, in my opinion. And second, is the experiment incompatible with semi-classical gravity? So quantum matter interacting in some way with the field theory, which is classical generativity, it is incompatible. And that's the two things together are quite surprising, because one tends to say, okay, but semi-classical gravity, of course, includes all non-relativistic quantum mechanics stuff. No, it doesn't. That's exactly the point, seems to me. But these are the two answers somehow. And I agree with what Mario said about that. Now, Czeslaw, you're referring to that debate. I remember it because I was part of that debate, and I argued very strongly in that debate. In fact, it repeated it with a French measurement with the neutrons and with the cow experiment. And at the time, I was arguing strongly that these experiments have nothing to do with general relativity. So I was definitely on the side of this has nothing to do with general relativity. Of course, you can give a general relativistic description if you want, because we have independent reasons to believe general relativity. So if general relativity predicted something else, it would be interesting, but it doesn't. Generally predict the same thing. So I don't think that if one wants to see the gravity entangled experiment as a confirmation of general relativity, that's silly. Okay, if we are in the frame of mind, okay, what we know is non-relativistic Newtonian theory. Do we say something more? That's not telling us anything more. If you're viewing this as a experiment telling us something about general relativity as opposed to Newtonian gravity, the answer is the experiment doesn't say anything. I think the experiment, Mario said that, I think the experiment, unlikely the cow experiment, unlikely the neutron quantum particles falling in the field experiment, unlikely those, says something very strongly because of what Eugenio just said, namely the cow experiment, the neutron experiment, are compatible as they are with quantum matter on a classical geometry. So quantum matter on a classical gravitational field. So if we take as a part of our information about the world that the gravitational interaction is brought around by a field, and this is a relativistic field, has degrees of freedom and so on and so forth. So if we include this fact in our knowledge, in the case of the cow experiment or the neutron experiment, nothing changes. We just have two alternative descriptions. If we do it for this experiment, bingo, everything changed dramatically, because now this experiment, it just doesn't work with just simple gravitational field or simple semi-classical geometry. So it tells us very strongly, unlikely the cow experiment, unlikely that quantum mechanics plus classical, what we understand about classical space-time, just is incompatible with nature. And that's unbelievably strongly. So I've been doing business of quantum gravity for 40 years, and I was always interested in experiments. So every time somebody said I have an experiment of quantum gravity, I was spending a month in Marseille, we were making relativity lunches, saying what the hell these people are saying. And every time it was, oh, come on, we're not interested in that. So it was very good, cow experiment is super interesting by itself, right? It's nothing to do with it. But not for quantum gravity. when I learned about this experiment, I learned from Sougato and the others. For me, it was changed from totally. Now, you said, oh, it could be a Newtonian interaction, or it can be a non-local Newtonian interaction, something we don't know yet. Of course, but that's, I think, everything could be something we don't know yet. But if it's something we don't know yet, it's even more interesting. What we know, what we know how to describe the world is this non-relativistic limit, and this is not incompatible with GR, and in a relativistic limit with classical gravity, and this is incompatible with the result of experiment. So the result of experiment rule out what we know. It's always possible that there is something we don't know. I mean, maybe it's just God coming out and establishing the... Okay. So this seems to me a completely different story than the cow experiment.
Yeah, I think Kaslav wants to comment again, but also Mario. So, but maybe I just quickly add, yeah, take the mic to Kaslav, yeah. But could I just add a few comments,
yes,
observations at this moment? So it looks like two things are there, and so one thing I find a bit surprising, though I use that, but I find it a bit surprising that, not surprising, but somehow you need both relativity and quantum mechanics to argue for the validity of this experiment. And of course, we can take as proof of relativity from other experiments. We already know nothing goes faster than the speed of light. We know the locality, but of course, people have not directly measured the causality of Newtonian interaction itself, right? So, but on the other hand, from speed of gravitational waves and things, we know that actually, information does go to speed. So we are having to use ingredients from a different theory, which in principle is independent of quantum mechanics. So this probably, I don't know whether it points to a deeper thing, that maybe relativity and quantum mechanics are just, whether they are built to be, have to be, complement each other in some way. I mean, it's a interesting. And the other interesting question is what is coming from Mario's, what Mario pointed out. I just wanted to re-emphasize that, is that somehow, so far we have how to picturize the Newtonian interaction or the Coulomb interaction in some way, right? Even when things are moving and dynamically happening. So our picturization has been that the two masses are exchanging, virtual gravitons, which is, so we get an interaction. We project, when we project in a limit that you can use it as a quantum field theory. You project the thing to vacuum, and you still get an interaction to second order in perturbation theory. That is one way to visualize, but of course this doesn't readily help despite its all relativistic treatment and everything. It does not somehow yet help in the causal picture. And then there is recent work with the retarded potentials by Markovich, which does give a causal picture. And I also saw this talk today on needing the longitudinal gravitons somehow. So I wonder whether, so I do strongly agree with Marius on this, that maybe we are getting some new new visualizations of the Newtonian potential, and whether this will help us in quantum gravity in low curvature regimes in some other way. That could be an interesting question. But now let's get back to Kaslav.
Yeah, I just feel that I was misunderstood, so I have to clarify. I didn't think that experiment is the analog of the cow experiment. It's going beyond cow experiment. I do think that what this experiment will show, that what mediate the interaction is in some kind of superposition, is a quantum. I have no doubts about that, and we can see that gravitational field will be in some sort of non-classical state. What I said, that if from this conclusion that we have a gravitational field in a superposition, you want to conclude that we have a superposition of space-time, it's an overclaim comparable with the overclaim that the cow experiment shows general relativistic effect Because in order to claim that this is a superposition of space-times, you have to measure space-time. You don't have it just structural as two particles. That's why was the proposal, maybe later on, or to think of a Gedanken experiment, in which one of those particles will be something which can measure time, like a quantum clock. And then we will see that this quantum clock will get entangled with that other thing. That means that, and we will see that this will be independently of the structure of the clock, of the interaction in which the clock is running. That would, for me, be a moment where we can go beyond a Newtonian interaction mediated by some mediator into the domain where I can say it's a superpositional space-time. That's what I want.
Okay, yeah, so there's, I think maybe Marius goes first and then I come to you. Yeah.
I mean, it was clarified. I just wanted to make a very quick comment. One way to think about this discussion. And it's the importance of the experiment too. So the question is, are we going to assume that the gravitational field is a thing or not, right? So if you do not assume it's a thing, there's nothing to say. Now, if you assume it's something, then this experiment forces you to say, well, this something behaves quantum mechanically. And that's the importance of the experiment. Now, what Czeslaw is saying, yeah, but this something doesn't have to be space-time. It can be some sort of Newtonian field that is in superposition. But I understand what you're saying. But on the other hand, the Newtonian field is not clear in what sense it is a thing, because it's just something that is given by a constraint, right? So I just wanted to make this point that I understand the operational argument about the clocks, but you have to somehow give way on also all the understanding we've built over the past century about what it means for the gravitational field to be a thing.
Okay, Eugenia, you had something.
Thank you. Yeah, thank you. Yeah, so I would like to follow up on this discussion on the debate of are we observing a superposition of spacetimes, and add one more example because Czeslaw already gave one more, and I would like to put it as a bold claim, something that I think I'm convinced of, that we have observed since long in an experiment a superposition of spacetimes, even though like not everybody agrees on this. I'm referring to the observations in the experiments of Kobe, WMAP, and Planck in cosmological perturbations. So I make first the claim, but I know that this is somewhat controversial in a way that is somehow, to me, similar to the discussion we are having here. So let me spell out why I'm saying I'm convinced and why my position is somehow different from many cosmologists' position. Generally, the claim is made that in cosmological perturbations, in a cosmic microwave background, we are going to see quantum gravity and gravitons once we measure tensor modes. Once we are going to see this spectrum of tensor perturbations in B modes. That's the expectation. It might come in 5 years. It might not come. It depends on how big they are. That's not the claim, or it's not what I'm speaking about. I'm speaking about scalar perturbations, the ones that have already been observed, the ones that give temperature fluctuations of 10 to the minus 5 with a spectrum that is known. The way this is generally presented in reviews and in textbooks is that these are fluctuations of some scalar field, and that's what we are measuring. That statement is gauge dependent, okay? You could do the same calculation in a gauge where you haven't fixed the metric fluctuation or the foliation of spacetime to be metric fluctuation with zero curvature, but another gauge that is the comoving gauge where there's no energy fluxes. In that gauge, you would say it's purely curvature perturbations. That's actually the name that people use. But can we make a gauge independent statement? And the gauge independent statement is that what we have is superpositions of spacetimes with the spacetimes that appear having a curvature that differ by a relative magnitude of 10 to the minus 5 with a slight small percent red tilt. And this is a gauge-independent statement. And so in that sense, I like a lot the way Marius phrased this gravity-induced experiment, gravity-induced entanglement experiments. That is, I don't necessarily have to say what component of the metric, is it a Newtonian mode, is it a longitudinal mode. Once I say it's superposition of spacetimes, that doesn't distinguish necessarily what component or what gauge I'm speaking about, but really says something about quantum gravity, about spacetime geometries. And so in that sense, I would say that the current observations that are at this point precision measurements are measurements of superpositions of spacetimes. And if one was to reverse the logic and say, could you have a metric that is completely classical and still be compatible with these observations? The answer is no. Yeah, and I wonder how many agree with this point of view. That might be bold. It's certainly not the standard cosmologist point of view, but I like to think that is the quantum gravity community point of view.
Okay, so thank you. So maybe I will like to make, so Carlos, so just let me make some comment related to that, and then we will pass on to you. So there are two things. So Eugenia, so you had two comments there. One is the gauge thing, that you do not necessarily have to see the transverse modes, the what you call scalar modes. Their quantization is equally important, and there these new works may be quite interesting, where we are finding this new relation that may help in an expanding background or something. Maybe some calculations the mathematics will not be different, but maybe just redone in a different way might be interesting. So that's a positive thing. On the negative side, what I want to say, so this I'm coming as a quantum information theorist, okay, or someone doing foundations of quantum mechanics, to tell something is quantum, you cannot conclude that from one basis, right? So measuring the curvature fluctuations, or any fluctuations. So there are also these recent works on detecting, noise of gravitons in LIGO, or anything. People might think that you have some holographic space-time noise or something, but if you detect anything in a one basis, it's like measuring in position basis, and you find a probability distribution, right? So of course you find fluctuations, but probability distributions are statistical mixtures. They are not quantum coherent, right? So measurement in at least in two different bases would be needed, and this basis is not in the sense of, so this basis is the quantum basis transformation. So you have to do it, so in some sense, just the measurements of curvature fluctuations alone, but if you kind of can get the momentum component of it, if this is the Q, then the P, okay, that would then be the thing. That will generally require you dynamics, which changes basis, so you have to be at different times, or see some entanglement in the sky, as some people are trying. Then that would be, so otherwise, like one basis noise. Now, of course, one can still try to make one basis noise very dependent on a theory, but then there are so many theoretical assumptions, right, of the initial state of the universe, the inflation. But I'm not a cosmologist, but I think there must be some assumptions, right?
Can I add exactly this? Because this is extremely exciting, and there is a discussion, and CMB is one snapshot at one time, and I completely agree with you. We would need a second snapshot. And in principle, the second snapshot is something we have, and people are studying, that is the distribution of galaxies. That's a second snapshot at much later time. It's too early to say if there's sufficient correlation, but that would go in that direction.
Yeah, no, that is interesting. That would do, but at the same time, one also have to see that these are highly now correlated. All these are like what we could call multipartite. So the correlations have to be very, carefully checked to conclude quantum nature here. Definitely at least two times. I mean, someone like Kaslov is an expert at something in the sense of what people call legged Garg or something. At least, yeah. So Kaslav, I will come to you, but since Carlo wanted to say something before, and then we will go to, thanks. Okay, so maybe, then.
Okay. It's a general comment. Somehow, I think these discussions are particularly interesting and particularly difficult also at the same time, because we're addressing these things coming from different sort of intellectual communities, which have both a different language, not just language in the sense of terminology, but language in the sense way of thinking about reality, and that give different things for granted somehow. And so assumptions are given for granted in a different manner, and problems are considered different. So we see various examples of that. If I work in quantum information in a non-relativistic setting, I ask question what it means to be quantum, which is a fundamentally different question than the question that the quantum gravity guys ask what it means for gravity be quantum. It's really a different question, because the question the quantum gravity guys ask is not what it means to be quantum it's just it's the collection of all ensemble of phenomena that we call gravitational, described by classical theory, or not. That simply that. And since the only alternative that is being explored, as far as I know, it's a quantum theory. It's that these are the two alternatives on the table. The kind of question that you ask when you say, "Is this quantum?" It's much more subtle, because this is the quantum information way of addressing the problem. What can I measure that? What is the thing that I call quantum? In quantum gravity, what was the thing we call quantum? It's just quantum theory, whatever you want to define it. Hilbert spaces, operator, or path integrals, or algebraic quantum theory, whatever. It's that thing there as an alternative, classical. Another example is space-time. I mean, Čáslav said, well, I don't want to call this space-time because it can be a gravitational thing and not be related to space-time. And, you know, in our community yeah, of course, but then this means that everything we have understood about gravity is wrong, which it's possible, but it wasn't given for granted that space-time is the gravitational field. In fact, that's Einstein 1915 great idea. If you identify in the community, space-time is a synonymous of gravitational field. We're going to say, well, fine, in another community, I call space-time something which is not necessarily related to gravitational field. So until I can make up the difference, I'm not talking about space-time if I talk of the gravitational field. I understand, but this is a different it seems to me a deep different of assumptions. And the same is about gravitons. I mean, if you come from a sort of theoretical physics environment where quantum field theory is about particles, and of course this is not a small little environment of theoretical physics, it's everybody doing quantum field theory at CERN and so on and so forth, plus also a good piece of condensed matter, whatever. Then you always immediately want something in terms of gravitons and virtual gravitons, and you say, that's what I'm talking about when I'm talking there. And then Marius come in and says, no, wait a minute, we're not talking about gravitons, because we come from a way of, somehow, in quantum gravity, and this has nothing to do with experiments. In quantum gravity, full quantum gravity, just gravitons are not there, because gravitons come up with perturbation theory around Cosby. So, so the immediate reaction of quantum gravity guys is, let's forget gravitons and forget photons. Let's look at the quantum properties of the field as a whole, asking questions about what is gauge dependent, what is not gauge dependent, and things like that. So this means, what I'm saying is that it doesn't seem that one is right, one is wrong. It seems that if we recognize what the others take as obvious assumptions, and what are not taken by obvious assumptions it's easier to and not somehow also, obviously nobody can claim my definition of the world is the right one, because nobody's definition, I mean, the words are used different in this context. Another example, and then I shut up, is locality. I think this has created an incredible amount of confusion, because if you come from theoretical physics, this in general, locality is not questioned. I mean, if we discover that, slowly, wait me to finish if we discover that the world is non-local, okay, in the sense a relativist would say, I mean, that would be like discovering that, you know, there's a preferred frame, or that energy is non-conserved. In quantum information, locality means something different. And everybody knows that quantum mechanics is non-local. So the reality is non-local, but the non-locality in that sense, the thing which is violated by the Bell inequalities, it's completely unrelated to the relativistic locality, which is the fact that in quantum information terms, signaling go on within the future light cone. So that's another thing which is confusing, because in the EPR experiment, in the gravity entanglement experiment, there's part of us which says, well, of course there is locality, because we know the world is local. And a lot of people coming from the quantum information community say, what these guys are talking about? I mean, we know that there's all non-local things. How can they just read out locality immediately when this is what we're talking about? So it's totally different meanings of locality. So I think we should be careful in this discussion to disentangle the different assumptions, the different language.
Yeah, very interesting. So let Kaslav now come with his point. So of course there are many things going on, being raised here. So we can probably continue also other things. But anyway, let Kaslav tell his point.
Yeah, I think we should stick to the scientific method to back up our claims only on the experimental data. And I think this experiment is extremely important, and it indeed shows that mediator is a quantum and it's a gravitational field. But I think it doesn't show anything more than that. Now, we can also say we know from other experiments and our theories that it should also imply the superposition of spacetimes. But I think this is a dangerous path to keep on in future, because you can go on and say, why do I need this experiment in the first place? Why can't I say, oh, I have a superposition of neutrons in an interferometer. A neutron is a massive particle. It produces gravitational fields. Therefore, we have superpositional spacetimes. I think we should be careful. I also said I have no doubts what will be this outcome of the experiment. But still, I'm not 100% sure. And I think once we make another step, just a little bit harder experiment, and we prove that this is true also for the clocks, then we say, oh, they show superposition of times. Not more than that. Then we go on with the next experiment. We may hope that on this path, we will get surprised at some point. And I think this is important to keep on your mind. But the reason I took the microphone is what I like this discussion that we went in the cosmology. And I don't know, I can stop here because I don't want to open a new one. If somebody wants to jump in, I was thinking about these experiments with 2 slices in time, but I don't want to abuse now. So.
Okay. So maybe would there be other sessions relevant to this? Maybe that time also this can be discussed again. Yeah. So there is some comment from yeah.
Okay. Good morning, everyone. I'm Carlos. I am from Mexico. I am from the National Autonomous University of Mexico. I have a comment expanding a little what Carlos said, because I think that we need to be pretty clear when we speak about quantum, because, and this is also connected with what Pierre said in his presentation, because what do we mean by quantum? When we speak about quantum theory, we are used to speak about operators and Hilbert spaces, path integrals, but if we want to ask, for example, if discreteness is an essential feature of a quantum theory or not, it is important to first define what do we mean by quantum, and what do you expect that gravity is a quantum theory? What distinguishes a quantum theory from a classical theory? What is a classical theory? For example, in the Thomas Timmans book of Modern Canonical Quantum General Relativity, he defines quantization as an homomorphism between a symplectic manifold with a Poisson algebra and a Hilbert space with linear operators. But that is a mathematical definition, and that uses very precise and very clear mathematical structures. But we need to define what is a quantum theory. I mean, if an alien comes from another planet and gives us a theory, how do we know that it's a quantum theory? Because of the scale that describes, because it appears h bar? Well, I think that we need to be pretty clear, very precise when we speak about quantum, because it's very difficult for me to find a precise definition of a quantum and a classical theory. What is a classical theory? What is a quantum theory? If I formulate a theory without manifold, without Poisson algebras, without Hilbert spaces, and I use other mathematical structures, is that a quantum theory? Is that a classical theory? I don't know. I think that is very important, especially if we want to distinguish if discreteness is a characteristic of a quantum theory, if entanglement is a characteristic of a quantum theory. I think it's very important to distinguish a classical and a quantum theory. And also another comment about one of the presentations that we saw today is that the discreteness of the area and volume operators in loop quantum gravity, because there is a little debate about this. I have found that some people say that we need to be pretty clear when we define the operators. We need to be able to define them in a diffeomorphism invariance way before to be able to say that they have a discrete spectrum. So that is very important. I know that there are people here that maybe is going to say that now they have a spectrum, a discrete spectrum, even if we cannot define them in a diffeomorphism invariant way. But I think it's very important to be able to make the things clear, to have a truly or a good advance in our development. Well, that's all that I wanted to say.
Okay, so there is something, a mic here and then a mic there. Yeah. So first here. Yeah. So I'm just quickly before I just want to add. So we in any given experiment we kind of test non-classicality. So when we say quantum, we are making a jump, and it's related. What is quantum? Is a lot of things together. Yeah, if you.
Hi. I want to give a relativist perspective on this discussion, between Czeslaw and the other, and also a quantum gravity perspective. So I totally agree with Czeslaw that the experiment which is described right now just, measures the superposition of the Newtonian potential. And Czeslaw is right to challenge people to just go further. So I want to go a little bit further and say, what would it take to make, the claim that it's a superposition of space-time? And for that, you have to understand what is the nature, what is the essence of the Newtonian potential from the GR perspective. Okay, so you can understand the Newtonian potential as just a subsector of the full GR, which is the subsector of static solutions. And then the Newtonian potential is just the norm of the Killing field there. Okay, that's the way to read. Now, if you write down the Einstein equations, you're going to have two equations that comes. One is the Newtonian equation, so this norm satisfies Newtonian equation, and that's the one that may be sourced by matter, and that's the one that people measure. Okay, but there's another equation, which is much more important if you want to describe the geometry, is that, and in fact it would be a harder challenge for experiment, because this other equation isn't going to be quadratic in the Newtonian potential. So there's a new equation that Einstein equation gives you, which is essentially something that says that the square of the differential of the Newtonian potential is proportional to the Ricci curvature of the background. Okay, so that's the one that you would have to measure to make the claim that Carlo makes. Without this, it's not quantum gravity. That's what I say. So, ultimately, since phi is small, the square of phi is smaller. And what is the principle at play there? It's the fundamental principle of equivalence that somehow says that the gravitational field itself is a source of energy, and therefore the gravitational field itself curves geometry, okay? And I think it's very important and basic that people understand the basics of GR before. And I think that completely settles the debate in favor of Czeslaw.
Okay. Yeah, so I think the next thing was there, but maybe I quickly add one thing here. So I did not fully follow, but one thing is that it's true that the entanglement does happen due to the curvatures. Right? The entanglement doesn't happen due to the acceleration, because it's due to the spread, so how different the gravity is between two parts. But yeah, so your comment here.
Hi, I'm Dane Danielson. I just would like to point out the fact that we have a effective description of these experiments, which is consistent with principles that are independently experimentally verified, like locality and causality, and this effective description is given in terms of linearized quantum gravity, just the theory of a linear perturbation off of a metric where you quantize the linear perturbation. And given that this effective theory is consistent with many of the cherished principles that we're talking about here, I think it can be beneficial or useful to interpret these experiments in the language of linearized quantum gravity. And from that perspective, it is it's clear that the Newtonian potential is just, or the Newtonian field is just part of space-time, and that these experiments are measuring superpositions of space-time. Now, of course, you can propose other, there may be other proposals, but I'd just like to point out that, given that we have a theory that's consistent with these principles that we're discussing, it might be useful, or it can be useful to interpret the experiments in the language of that fully consistent, albeit effective theory.
Yeah, thanks. Yeah, so I agree with that 100%, but of course there are other views as well. And I mean, yeah, so any description which is correct is all right. So you wanted to say something?
Yeah, I wanted to throw in an observation coming from the philosophy of physics community about actually this issue of interpretation of general relativity vis-a-vis, is it a theory of space-time? Working back in observation, I believe there's a Nick Huggett's talk about, there's kind of two ways you can think about general relativity. You can think of it as a theory of space-time because you really have this spatiotemporal structure that gives the behavior of ideal rods and clocks, and real rods and clocks track it. Or you can think of it along the lines of an effective field theorist, that you have this universal coupling, and real rods and clocks are physical entities, so they're going to behave in some way such that you get time dilation, so differential readings in these physical processes. And I think that's relevant for thinking about this issue of, would the gravitationally induced entanglement show us that space-time itself is quantized? Because if someone is attracted to the Harvey-Brown style, which is this latter option, that real rods and clocks behave in the way described by GR because of universal coupling, there's space here to resist the move to say space-time is quantized because this gravitational interaction is quantized, precisely because it is not obvious that this degree of freedom of exchange of energy and momentum gravitationally is quantized. It is at least not obvious that a consequence of that, a logical consequence of that, is that readings of clocks have to be quantized, that there's some limit to how what the readings of your clock outcomes would be. It seems in principle compatible for those outcomes to be continuous. So anyway, there's room in logical space where someone is attracted to this universal coupling style interpretation of what GR is to resist ascriptions of the quantization to space-time structure itself.
Okay, so I think maybe we can come back to these topics again. Perhaps I just diversify a bit because I see it's like the first topic already was going on, and to be fair to all the speakers also, so we haven't discussed much about the experiments at all till now. So obviously, I'm well aware of many difficulties in the approach that we propose primarily. But I think that the major issue is the creation and maintenance of the superposition. That's by far the main. And here, maybe I would like to point out this non-Gaussianity which came in Richard's talk. So in case of larger masses than these buckyballs so far, the achievement, great as it is, which has happened is people have cooled to ground states of harmonic oscillators, right? And you may also squeeze or anything, but that will not yet prove for anything which is a Gaussian described by a Gaussian state. You always have a description with full positive probability, which is the Wigner function is not negative. So in some sense, you really require some kind of, I mean, of course, in our experiment, we are just preparing by hand, but one has to show at least, even for these masses, any mass larger than the buckyball, one has to show any evidence at all of non-Gaussianity in the first place to even, so a requirement of these things are at least the masses in our experiment or the atoms in Richard's experiment they are quantum. That's a preliminary requirement. So one has to show some kind of non-Gaussian states of these ingredients first in this scale. That is, I think, still lacking. I don't know in the BEC side whether some non-Gaussian states have been displaced, but on the mass side, definitely nothing beyond buckyballs have been shown to. Yeah, so Richard, do you want to comment? Have people seen any, like?
Yeah, I mean, I agree with what you say, Sougato. So just on your comment about non-Gaussianity in atoms, as far as I'm aware, that hasn't been done. You haven't seen non-Gaussianity in BCs. I think people are close, but right. Looking at it from the electromagnetic point of view, of course, right. Not from gravity.
Right.
So people have measured in cold atoms essentially non-Gaussianity, but not in a BEC state yet.
Right.
But it's not far away.
Yeah, so cold atoms would be like the similar to the techniques that probably we propose. I mean, our techniques were borrowed from ion traps in some sense. And also I think in light, with light people have shown in microwave cavities, but again, interacting with qubits and things like that. So I think that is a big gap to fulfill. I'm just telling that the next stepping stone in that direction would be to show, I would say, non-Gaussianity in mass, a nanocrystal, or any non-Gaussian state of a BEC would be big next steps already before anything else is done. So that is one important point. And the other thing I wanted to ask, this is openly, so this little bit of that was raised by...
Sorry to interrupt you. I just, it's a good opportunity. I want your opinion. Do you think Richard's idea is a stronger test for the quantum nature of gravity than mediated entanglement?
Okay, stronger or weaker? That is a controversial, stronger, weaker, or same. So I would think it would be equivalent because the non-Gaussianity is kind of an entanglement. If you took a first quantized picture, people do not normally use first quantized picture. People use second quantized picture. So if you use first quantized picture to represent two electrons, then you have to use pseudo labels I and J, and they would be entangled. So non-Gaussianity is that kind of entanglement. If you took all the atoms in the BEC as with false labels I, J, K, L, then they would be a huge multiparticle entangled state due to this gravitational interaction. But even if they're indistinguishable, you can check for the non-Gaussianity. So stronger, weaker, I don't know. I think so. Was there a statement in your paper regarding not requiring the locality or something like that?
Yes, yeah.
Okay.
I mean, I think I'm not sure it's either stronger or weaker. I think I would say because it has, in my opinion, advantages and disadvantages.
Right.
So I think there was a comment that there's no need to, as far as we can tell, to assume locality of interactions. So that is a potentially stronger statement.
Yeah, I think, okay, so let me a little bit comment on that particular aspect. So it depends what one also means by, so as I'm saying, locality could mean, so as we do quantum field theory, everything in one position. Fields interact only when they're in the same position. But we also know there are Lorentz invariant models which are non-local, okay, like higher curvature theories of gravity and things. So they are slightly non-local. The spread is obviously, if it was drastic, we would have detected such changes. So I think I kind of interpret this locality more. I mean, these days I may go back, but these days I interpret more as the thing coming from the the gauge principle, that you need a field to interact with the matter to have a consistent gauge invariant thing. So the mediator becoming important is the locality. So the locality is in Hilbert space in some sense. So you need a mediator gravitational field between the matters. So and at that aspect, that assumption is also needed if you are doing the BEC thing, like not necessarily a spatial locality, but that the atom interacts with the gravitational field and the gravitational field interacts with the other atom. Yeah. So that aspect is, so I really wonder that aspect, whether it does come really from the locality, spatial locality, or does it come some way also from gauge invariance, gauge constraint, that you need, in like in EM, we know just with the charges you cannot make a, maybe Carlo wants to say something on that. Right? Yeah.
I think the locality you're talking about is a property of all the field theories we know. In the formalism, it is often convenient to use non-local things. And typically, when you gauge fix and you split, for instance, a transverse and longitudinal thing, you introduce a non-locality in the object in the formalism. But somebody else could not do that and just use a local language all the way through. And I think this is part of the source of the confusion. All the non-locality people talk about in the formalism, like the longitudinal part is non-local. It's nothing to do with reality. I can always define something, a variable, which is the position of this pen minus the position of a car far away. That's a non-local variable. It doesn't mean that the pen and the car interact. It's just my definition. So I think that the non-local features that appear in some gauges are artifacts of the formalism.
Okay.
Can I make a general point here? Because that's maybe, again, one of these cultural facts. There is one way of viewing experiments as what are they telling us specifically new. But there's one way of viewing experiments as confirming theories of disconfirming theories. A theory predicts an effect. If this effect is measured, my Bayesian confidence in the theory goes up. If the theory predicts an effect, the experiment is not confirmed. Maybe Popper would say the theory is falsified. That's maybe too strong. I mean, my confidence in the theory goes down because maybe I'm missing something and this kind of thing. So I do understand that there's another way of thinking, and people like this other way of thinking. Like just experiment what they tell us. How can I read out of the experiment something a priori about the world theory dependent? But I think a large part of physics is done in the context of theories. So I have this theory and give me prediction. the measurement of Higgs at CERN could mean all sorts of things. It could be interpreted in 25 different manners. The point is that there's a consistent version of standard model that predicted it, and bingo, came out right. So from this perspective, I would say, and I'm curious how people react to that from different communities. Today, in fundamental physics, we have three parts of our knowledge of the world, which has a standard model, including neutrino mass and cosmological constant. The quantum theory, in the sense not relativistic quantum mechanics, just quantum theory as Dirac defines it, just that way of dealing with variables in various formalisms which are essentially equivalent in the relevant case, and classical general relativity. And we are in the curious situation, and I think it's worth stressing that absolutely everything we observe in the universe, with the possible exception of dark matter, but even that is, we're not totally sure, just follow from this series. Or we don't have any strong evidence that it does not follow from this series. Which of course does not mean that these theories are final, definitive, and there is nothing else to learn. But it's remarkable. I mean, rarely in the history of science we've been in a situation in which we have a set of basic equations, and we have no reason to believe that everything we measure, absolutely everything, absolutely, which doesn't mean that they end science, of course, because condensed matter is an open problem. But nobody questioned that condensed matter just follow from the Schrödinger equation, which is a part of QED and so on and so forth. So from this perspective, classical general relativity, a world described by classical general relativity, so locally more or less are Minkowski, quantum field theory there and the standard model, in this world, your experiment would be the first thing going out from this. Just not accounted by that. This doesn't account your experiment. So it will be the first thing that says, no, that set of fundamental theory is missing something. There are a number of attempts to write a quantum theory of gravity. I mean, look, quantum gravity is one. There are, of course, many others. All of these do predict this effect. So in this sense, it seems to me, they don't show that any quantum theory of gravity is right. They don't show, but there's nothing else on the table. That's the point.
Yeah. So maybe I also add a comment here. So it's which way you're trying to go. That is so one is that you have a set of theories and some assumptions of initial conditions or something like that, and then you get some predictions, right? And what Carlo is saying that the largest classes of theories, almost any theory which has tried to quantize gravity and I mean to well-studied things such as loop quantum gravity or string theory. I would also ask simply the philosophy of effective field theory. So suppose we don't even know what the theory is, but still these works at this low energy scale, the perturbation. So everything does predict this observation. So that is going one way. Okay. But there is also, so in quantum information foundations, we are accustomed to going, because it's historic from Bell's point of view, we are accustomed to going the other way. So given this evidence, what is that we can rule out? Like we rule out locality.
This seems the core of the different. Yeah, exactly. That seems the core of the difficulty of talking. It's a different.
Yeah. So this is like all what I mean. Reminds me, it's a bad analogy. You know, the eigenvalue problem and inverse eigenvalue problem. Inverse eigenvalue problem is very hard. Okay. And it's also related to the point that you raised. So essentially, in different experiments, it might still be easier to say non-classicality that you cannot explain. Again, your definition of classical then has to be, that is also, people have stretched examples of definitions of classical as well. But it would be good to, so only thing I would add here, one should not just take the entanglement experiment as the thing to go back from, but all these other observations that we know, which we know from other experiments together. Yeah, Marius, you wanted to say something.
Yes, I don't want to monopolize the discussion, but actually I wanted to go back to what Eugenio was saying. And then, Carlo, you made some comments because I think there was a bit of a misunderstanding there. So the answer to you were asking us, so I don't know because of what Sougato was saying, right? And I'm actually very curious to see what the quantum information people are saying. So, Carlo, I mean, also when you want to test the violation of Bell inequalities, you need to do measurements in two bases, right? This is not about talking about non-classicality or what is quantum theory or what. It's just that you can create that with only classical correlations. That type of measurement outcomes. So that is what I don't know whether the fluctuations of the scalar fluctuations in the CMB can be taken to be the same evidence as the induced entanglement experiments. And I'm actually very curious to know if that evidence is out there already or not.
Kastler want to say something or somewhere else before or okay. So I think Richard and Kastler raised their hands same time. So maybe I go with Richard and then I come to you. Yeah.
Okay, just to be quick, I mean, people have looked at the scalar perturbations as whether it is evidence of quantum gravity in the quantum information community. I mean, there's not a lot of work at it, I don't think. As far as I'm aware, the conclusion is that from the quantum information point of view, it is not enough. It's exactly like you say, because you need to have two measurements in different bases, and that is the problem. I mean, I think there's some idea when maybe there's a different way in which the universe has expanded that you can somehow access. But it's to do with the decaying mode of the CMB, if people are familiar with that. And I think there's some idea in how, like, if there was something a bit strange, then a very unusual model of the universe, then perhaps you could access both. But in the one that we seem to live in, that is not possible. But anyway, I think it's only early stages of what people are looking at in terms of quantum information and the CMB, and I think it is a very interesting avenue to explore further.
So Kastler has something, then I'll come to you.
Because we restart this discussion. So indeed, like you think, you have no choice of the measurement basis apparently in cosmology, but the thing that was already said in two slices and so on, if you think about the free evolution of a quantum particle, so if you measure in near field, you measure position. If you measure in the far field, later on, you measure momentum. So by taking two slices in time, whatever it could mean, you can actually effectively measure two bases, although you have no direct active possibility to change the basis.
So this is an interesting, important point. Of course, it's coupled to the fact that also inside your horizon, everything may be multipartite entangled as well. So that's yeah. I think Eugenio wanted to say something also. Oh, hi, Rob. Hi.
Yeah, hi. So I wanted to pick up on something that was said earlier by Carlos concerning, what is quantumness. I think it's important in a lot of these discussions, we sort of fall into the trap of thinking we all agree what quantumness is. So I think the important thing is to realize that, an important part of this discussion is to, be explicit about what we think, it means to show that something's truly quantum. And it's important to note that I think right now, in different communities of physics, very different definitions. A quantum field theorist might say, oh, if the path integral is focused on one path, then I'm going to say it's classical. If it's not, I'm going to say it's non-classical. Quantum opticians will say, oh, if the Wigner representation is positive, then I'm going to say it's classical. If not, it's non-classical. A quantum information theorist would say if everything is diagonalizable in one basis, it's classical. If not, it's non-classical. And these are all different definitions. And so it's important to, I think, they can't all be right to some extent, that it is a good idea to have a discussion about what should we call quantumness. And so I think the quantum foundations community, even within itself, argues about what should count as quantumness. You know, there's not even agreement there. But there are some sort of more stringent notions and less stringent notions. One comment I would make is that in the face of disagreement, if you know, two people can't agree on what quantumness ought to be, then I think the field of quantum foundations provides a good route for how do you make progress in that circumstance. And this is I think the high road, which is you prove a no-go result. You say, all right, look, here's my notion of classicality. All right, I'm going to lay it out for you formally. Here are some background assumptions, or you know, here's some principles that I think are reasonable. Maybe locality, you know, maybe something else. And now I'm going to prove that there are certain operational features, things that we could all agree upon, things that would arise in an experiment, that if we were to see them, it would show that one of those assumptions has to be false. So that's the model of Bell's theorem. And what's beautiful about Bell's theorem is that, you know, you go to the lab, you violate those inequalities, and now we can have a discussion about, you know, which of those assumptions must be wrong. And so if we disagree about what the notion of classicality is, we can have an argument about the assumptions. What's bad is just saying, look, I think this is non-classical because why? Because I don't see how to explain it classically. And there's a lot of that, which is just, oh, you know, I use the quantum formalism to derive this, therefore it must be non-classical. But that's too low a bar because, you know, so many things you can derive in the quantum formalism, it doesn't prove that they can't be explained classically. So let me give a few examples of what's come up. So, you know, discreteness has come up. Is discreteness necessarily non-classical? Well, no. You know, classically we have standing waves. You know, a guitar string has discreteness. Discreteness is not a proof of non-classicality. Or even entanglement. Entanglement on its own is not a proof of non-classicality because there are parts of quantum theory that contain entangled states. If the set of measurements I can do is too limited, then merely have entanglement doesn't prove that I can't explain the whole thing classically. So for example, Gaussian quantum mechanics. Lots of entanglement there. It all admits that positive Wigner representations can be explained classically very easily. So, you know, that's why in a Bell experiment, not only do you need an entangled state, you need to do specific types of measurements on the two wings to prove that there's no classical model. And I would say the same thing, that the idea we heard concerning non-Gaussianity, I don't know the details of that proposal, but again, you know, if I do an experiment that just involves number eigenstates, right? I prepare things that are diagonal in the number eigenbasis, and I do measurements that are diagonal in the number eigenbasis, well, there's clearly a classical statistical explanation, but if I write it down in the Wigner representation, there's lots of negativity all over the place. So it's the negativity together with, you know, it's the fact that there's no quasi-probability representation that stays positive for all of it. So I think, you know, it's important to sort of try to be very clear about what the assumptions are that the experiment would then prove, you know, one of them is falsified.
A very good comment. Yeah. So, Carlo, before you, maybe Eugenia was waiting for a while, so let him have his chance. And then, yeah, it's a very nice. Okay.
Yeah, I want to react to that and strongly to one part of that, of what you said. I appreciate this perspective. I think it's interesting. I think that this kind of research is interesting. And what I disagree with is this idea that either I think reality in this way or everybody else doesn't know what is talking when they're talking about quantum. That, I think, is wrong. Because there's a completely different perspective about this issue, which is a viable perspective, and it's also discarding a priori, which is the following. And I would like to know, where do you disagree with that? I know three kinds of theories, okay? Theories expressed in the language of classical mechanics. There's a certain possible variants. There's Newtonian, there's Lagrangian, there's Hamiltonian, there's a phase space with Hamiltonian. And there's a number theory that describes the world very, very well that fits that scheme. The classical electromagnetism, Newton theory of the solar system, a classical pendulum. Then there's a second class of theories, which is quantum mechanics. And they all have the same structure. Again, can be formulated with path integral, with Hilbert spaces. Okay. And they all say in the axiom of Messier, including quantum field theory. And they have a number of funny phenomena, which some of which we know cannot be reproduced by classical. And that's a second class of theory. And we know that there are many facts of the world that are very, very well described by quantum theory. Okay? Then there is a third kind of theory, which is theories which are neither one case nor the other case, nor the other case. It might be interesting. I don't know. I'm not God. I don't know. For the moment, they haven't explained anything. I don't know any single phenomenon to explain, which doesn't mean that this theory cannot be interesting, but for the moment, I don't know any phenomenon which is real phenomenon measured in the laboratory, which is not explained by either classical theory or quantum theory, which means that explain the quantum theory within a limit or not within a limit. So this is a perfectly clear statement of what one means by classical, what one means by quantum mechanics, and what one means by saying, oh, that particular phenomenon, I'm not able to explain it in classical mechanics, but I meant to say in quantum mechanics. The perfectly clear meaning of what it means to be quantum mechanical. It means to be described by a theory in which there happen to be all sorts of phenomena which a great part of the community study one by one these phenomena and what they are. Now, that's the logic of a lot of people. Now, the fact that you come from a different logic is perfectly fine. You come from a different logic and say, I don't care. I don't want to admit the theory first. I want to say, well, there are some funny things, Wigner functions, negative, blah, blah, discreteness, blah, blah. Which one do I want to call quantum? Is that a question? I mean, call quantum A, quantum B, quantum C. We don't have to fight on what we call what. If you want to call quantum when there is a sort of kind of interference, fine. Well, different criteria of being quantum. I mean, everybody choose a criterion, and then we see whether they're equivalent or they're not equivalent. But why dismissing the simple logic, which is we know classical mechanics and theories within classical mechanics. We know quantum mechanics and theory within quantum mechanics. These are the two that explain the world. We know the relation between the two because one approximates the other in some regime. And we're open the possibility that there's a third possibility. So we know exactly what it means to be quantum. It means to be described by theory which is in that structure.
Maybe should we let Eugenio do his comment and then we go back to you, Rob? Yeah.
So I would like to go back to the experiment. So if we want to continue the discussion.
Okay. Then maybe, yeah, Rob.
But I do have questions about the experiment.
Okay.
So I guess what I heard from your description is that let's take those theories which have proven themselves to be empirically adequate in some respect in the past, and so there'll be some classical theories of that type, some quantum theories of that type, and then let's try to adjudicate between them in different circumstances. And there's a third, right? So I think the main difference between our points of view is that I would say, the more interesting question is not, was there historically a theory that people wrote down that explains some phenomena, as opposed to, is it conceivable that there is a theory that embodies the principles of a classical worldview and can explain this phenomena? So for example, I don't know of any textbooks having been written about a classical theory of Dirac fields. I can write down the Lagrangian for a Dirac field, and I could imagine writing a textbook about that. Historically, people haven't done that, right? Dirac fields show up in the quantum context. But you could have imagined somebody writing down a classical theory of Dirac fields. I think it's important to find out, what is necessary for explaining a phenomena, regardless of whether that was put forward as an empirically adequate candidate for describing some phenomena. So to some extent, we're interested in a broader landscape of theories. Like, consider all the theories that embody a classical worldview or classical principles, where we can fight about what the classical principles are. But I think that's the main difference, that when we talk about proving non-classicality, we don't mean this can't be proved by the empirically adequate classical theories of the past, of which you can find textbooks in the library, but rather any theory embodying these classical principles cannot explain it. That's what Bell's theorem does. It doesn't assume, a phase space in a particular kind of Hamiltonian. It just says, look, as long as the theory is described by sets and probability distributions over those, I can't, and I have locality, I can't explain what we see. And I just make a final comment about, is the question of, what is quantum merely semantics? To my mind, there is no more important question than what is quantum. Is it worth fighting about this? Absolutely. Because, we want to understand what parts of our classical worldview are wrong by virtue of quantum theory. And we can't all be right. So I think, it's not just a question of, oh, let's call that quantum A, let's call that quantum B. No, somebody's going to be right about what the essence of quantum mechanics is. And I can't think of a more important question.
Yeah, but I'm not at all disputing your research program. I was only disputing when you say, oh, people who are not interested in understanding the deep essence of quantum and the kind of questions that Bell was interested in and you're interested in, those people don't know. When they say quantum, they don't know what they mean. No, I mean, I think there's people who figure out QCD, people who figure out QED, people who figure out the starter model, they knew exactly well what they meant by the quantum theory, what they meant by classical theory. They mean a certain theoretical structure with a certain properties that you want to understand better. Great, you want to understand better. And somebody might be interested to understand quantum gravity, thinking that quantum gravity is not the problem of what is the deep meaning of quantum. There's a problem which is interpretation of quantum mechanics, understanding what we mean by quantum. There's a completely different problem, which is do for the gravitational interaction what Gross, Wilczek, and did for the strong interaction, and what Salam and Weinberg did for the weak interaction, and what Dyson and blah blah did for the electromagnetic field, namely write a quantum theory and see whether this quantum theory predicts some phenomena which are not predicted by what we know is the classical theory of electromagnetism, the classical theory of so it's two different research programs which are both interesting and noble, and it seems wrong to me to say that we should necessarily mix them, and asking about the quantum gravity phenomena has to do with the interpretation of quantum mechanics.
I think maybe Bob wants to add something, and then
so
because
I think it's not just about two options. I think there is a fundamental deep distinction in belief between following Rob's suggestion, in which camp I am also, and following your suggestion, where actually I also would say Lee-Smolin, because part of what I'm going to say is something which came up in a discussion between Lee-Smolin and I. So there are people who believe in Hilbert space. And if you believe in Hilbert space, you're perfectly happy with an idea. We've got these quantum theories based on Hilbert space. There are people who actually don't believe in Hilbert space, and you're in good company there if you do, because you're in the company of Neumann, who himself rejected Hilbert space a few years after the publication of his book of quantum mechanical Hilbert space formalism. And if you don't believe in Hilbert space, you can't just say, okay, quantum mechanical means what we describe by Hilbert space formalism. So then you have to go somewhere and try to identify what are the features that really make things quantum mechanic in absence of a Hilbert space description. These things have practical consequences too. People have been trying to do this with Bell inequalities, which is a description free of Hilbert space, and that even have an application in cryptography and all that. There's the whole quantum logic thing where people try to characterize alternative to quantum mechanics. There were different versions. What I'm doing with the category theory is kind of the same. We're looking for something which produces most phenomena, quantum phenomena, but without going into Hilbert space. And also Rob has been probing like alternative theory. That's a way to do this. Just you pick alternative theories and you see how much you can actually get from quantum mechanics out of it. So it's really, like I said, Lee-Smolin at some point, we had a discussion with him, he said, you guys don't believe in Hilbert space and I believe in Hilbert space, but by not believing in Hilbert space, you guys actually end up doing interesting stuff. Because we have to explore new things. I think that's the big tension, believing or not in Hilbert space.
So
this is super interesting. Okay, it has to do with understanding quantum mechanics. Okay, there's another problem, which is what are the quantum effects in electromagnetism? What are the quantum effects in strong interactions? What are the quantum effects in gravity? Two different problems.
2 hours now, right?
That's what I'm saying. So you cannot. This is super interesting things what you're doing, but it doesn't mean that Weinberg was wrong when he was doing Weinberg-Salam model. It's nothing to do with that. And he was doing quantum theory. Not asking the question, the interesting question that you're asking. And I think one can do the same for gravity.
Right. So maybe we diversify a bit, and then I'll come back to you because it's the experiment related question, right? So your questions are
yeah,
related
it's
to the current
related. Yeah.
discussion.
So I think what is important here is that some people think that quantum theory still has a deep foundational problem, which might be relevant to this discussion. So that's why it's important to assume this perspective that Rob was talking about, because there might be alternative explanations that maybe are relevant for this phenomena. So if you don't believe that these alternative explanations are not relevant to explain this phenomenon that we're talking about here, okay. So I think that's the core of the discussion. That's why it's important, this kind of approach, right? To try to see the possible alternative explanations, right? And to see if they're relevant. You see what I mean? You need to take into account that maybe, if you are a collapse theorist, of course they are a little bit, or if you believe in Bohmian mechanics or in another approach, who knows? It might explain better this phenomenon in some sense. I think that's the core of the discussion here. Some people will say, okay, quantum theory is fine as it is, and we can account for this phenomenon with quantum theory as it is. Others say, okay, maybe this is where the measurement problem is important, right? And this is where we need to. And so I think that's this approach of Bell might be relevant to this kind of phenomenon to try to discriminate. Yeah.
Okay. So Flaminia wants to say something.
Okay. So sorry, Eugenio, that we are not letting you ask. So no, I just wanted to make a comment, and this is that I think that we always get stuck on exactly the same point, which is this discussion between what is meaningful to ask in one way or another. And Czeslav's comment on whether from the superposition of gravitational fields we can deduce or not, and his answer was not. The fact that we have a superposition of spacetimes is, I think, exactly, so the point of disagreement is exactly the same, because what Czeslaw was saying, but also what Rob and Bob, what they were all saying is that we should have no ontological commitment on what the theory of gravity looks like. And what I would like to stress here is that we are not saying that the approach that you're saying, that you believe in a Hilbert space and you have a quantum field theoretic description of the gravitational field is useless or is wrong. We are just saying that there are two different perspectives that can help each other and that can complement each other to ask a broader set of questions. And for each one of these two methods, you have a price to pay. And in particular, the price that you have to pay if you use this theory-independent language where you do not assume your theory is that you lose the fine details of the mechanisms, which is also what Lingqin talked about, and also all the other people, like what Sougato has done and what also Marius, you, and this is also very helpful to understand. But what we are saying is that there is a different way of understanding that can also be helpful, and we are saying that this is helpful because we have support from all the results that derive from the intuition that Bell theorem gave us that has helped a lot in a different context. And so, yeah. So I just wanted to say that there is an interplay between these two, and that using both things can be helpful to converge.
And so maybe we should not get stuck really on saying, oh, but this way is better than the other one, but maybe just embrace both and just try to go on together.
So just to make progress, maybe we'll have quick questions. Eugenius has been waiting for very long, but there are, I think maybe this topic is invoking a lot of questions. So then, yeah, you don't want to say now? Okay,
yeah.
You just say now. Yeah.
Okay.
And then we will come to you and Francesca also. But I think, yeah, before you, yeah.
Thank you, Sougato. Yeah. This was a really interesting discussion. I didn't want to interrupt it. I would like to go back to the experiment. I have a question for the people who thought so much about the experiment, and it's about coherence length and about, well, the fact that we know that often as theorists we make simplifying assumptions that can be overly naive, but sometimes we are lucky, and I want to understand if we are lucky here. To be concrete, because I don't know how to translate it exactly for this experiment, there's another experiment that I've thought a lot about some 10 years ago, where I see clearly where there is a possible difficulty that I want to see if it's addressed here. That is a proposal for a tabletop experiment with Bose-Einstein condensates to measure quantum gravity effects by having a condensate that is elongated in a trap and looking at the gravitationally induced lamp shift. So this would be a quantum gravity measurement of coupling of the condensate to gravitational perturbations. And quite surprisingly, the naive estimate is that if you have 10 to the 8 rubidium atoms in your condensate, and the trap is elongated enough, like getting to 5 centimeters, then the shift in energy levels due to quantum gravity alone, it's a GH bar effect, is 1%. So this would be, well, not measurable in 2010 when it was proposed. I'm speaking about a proposal of Bang, Bingman, and Mendonça. Probably not measurable yet, but very close, speaking about 10 to the 8 atoms in a condensate. So what is the catch? What is the difficulty? Why this has not been done? And what I understand is that when I learned Bose-Einstein condensate, I learned this idealized version of the condensate, but the one that you actually make in the lab is actually a condensate with a coherence length that doesn't necessarily include all of the atoms that you put in your trap. And so what I want to understand in this gravity-mediated entanglement experiments is how important is it that each one of the masses that you are entangling, you can consider it as really with coherence length over the sides of that body, and not smaller sizes, so that the estimates that we are making, they are not for the actual objects that are being entangled, but only for the constituents or for the patches of those objects. I don't know what is the status, and I would really like to understand, are we lucky? Are we close to that? Are there things that need to be done?
Okay. So that is something I can personally answer quite a bit, and then maybe I think other people can pitch in, like Richard and others. So we know only through the known effects that we know are there. We have tried to estimate them and found the conditions. Okay. And has been, it's not our work. It has started before, because people were trying to create quantum superpositions anyway for a while, right? So what we clearly know is the two of the major noises. One is any atom hitting any one component of the superposition. That immediately gives you a which way information, right? So pressure has to be low, okay? For the kind of regimes that we demanded in our original paper, the pressure is 10 to the power minus 16 pascals, okay? Which has only been realized in one experiment ever before in the world. This is Jerry Gabriel's experiment with penning traps. So it's a very hard pressure, never been realized anywhere else, okay? But in principle possible if you give sufficient effort. So one is that. The other is emission. The masses need to be internally very cold. So the emission of radiation from them can also give you Witch path information, okay? So internal temperature cooling needs to be to about 1 Kelvin. Okay, this is an important challenge, because the way at the moment people trap things and cool things are in optical traps, they get heated up. So this is a bit open, how to cool that internally so that they do not emit a microwave photon with black body radiation to tell where it is. Okay, These are two things which were known when we wrote our paper, but later we realized, due to criticism by someone else, we realized that even fluctuation of nearby masses, positions, so there is a gravitational noise background as well, okay? So the small g has to be 0 to the extent of 10 to the power minus 15 meter per second square, otherwise they will do random shapes. So for that we have proposed some solution of putting the experiment in a freely falling lift, and even after that there is noise due to the curvature, okay? So we have to keep things like snails and humans 5 meters apart, and then other things even more apart. So there's an estimate, yeah. So these are things we know, yeah. Now the question is whether there are unknown noises. We don't know. I mean, so when experiments start doing these things, they will probably discover more noises than we know, right? That's the thing. So these are the known from the known sources. We know the degrees of things you need to do in order to achieve this. Of course, in our experiment, we are just saying freely falling, but it would be good to do it approximately freely falling, like in a pendulum or something. So a lot of calculations need to be done, but I think, yeah, so these are from what we know. We know the temperature needed to be cooled, and there is also something else, which is charges inside the thin patch multipoles. So that is not fully solved. That can probably be solved by physically spinning. So we have looked at, not fully looked at that yet, but other things are telling that you can, I mean, these pressures and temperature are achieved elsewhere, but not in the same kind of experiment. I don't know, in the BEC context, where like the proposal which Richard proposed, I guess is the cancellation of other forces, but maybe you can comment on that. What is the status?
Yeah, I mean, that was a very detailed, rigorous answer, so I can't say much more. But I mean, for BECs, the problems are probably a bit elsewhere and also the same. So with the BEC, obviously, we can cool them to their ground state and they can stay coherent for to minutes, as far as I understand it. That's probably the maximum. Obviously, to test quantum gravity, you have to then push these results, and so you have to get slightly higher masses, probably 10 to the 8, 9, 10, which people think should be achievable. But then, of course, you also need to maintain the coherence of these things, and so it's a challenge to maintain a large BEC for 1 second or so, which is what you'd need. But it's the same, similar sort of decoherence mechanisms to the thing in the BMV as well. Like probably the particles in the atmosphere is the strongest one as well, I suspect. But you need a very strong vacuum in order to maintain this coherence. You also, as with the BMV, you have to, well, it's ideal if you prepare a squeezed or a quantum state that's like an entangled state, or entangled state in the BMV or a squeezed state in the BEC, because then you can use the quantum metrology to enhance the effects, but that then also can be more rapidly decohered, so that's another challenge. In terms of the BEC experiment that you suggested, I don't know enough about it to comment on what the challenges involved are in measuring the lamp shift from gravity.
So during the lamp shift, maybe I can add one thing. So what Richard has proposed is bit like a lamp interaction, you know. So is the second, like you interact with something, that so you get the square. But you are saying there is a kind of a first order effect when you trace out the gravity. So actually I have not looked at that. I will have a look at that proposal. So there are, okay, so there was some comment from you, right? There.
Yes, but it's more connected to the discussion before between the theory confirmation and quantum foundations kind of parallel. So I don't know if this breaks the conversation now. Can I?
Yeah, sure.
Okay. So I wanted to, my point kind of echoes Flaminia's point, which is what I find interesting about the discussion around the GME is that we were discussing two different ways of looking at the result. One is from kind of the more traditional theory and confirmation point of view, and the other one is from the quantum foundations theory independent point of view. And what I find interesting is from the theory confirmation perspective, what the GME says is clear. There are these theories like semi-classical gravities that will be ruled out, and other theories like a low-energy effective field theory will be confirmed. So you can increase your credence in these theories. From the quantum foundations point of view, it's less clear what is going on. And I think part of the discussion, part of the controversy starts from Sougato's paper and Mallet and Vedral, where they actually called up this theorem, the LOCC theorem, that classical communication cannot create entanglement, to put more strength behind this experiment. And I think the difficulty here is that it's not clear if the assumptions of this theorem, how do they map to the theories that we know, for example, quantum field theory. And I think there's some work going on. We're studying this with Marius, but also Flaminius and Galli's paper. They were looking at this, like, do all the theories that we know and use, do they satisfy the conditions of the theorem or not? Can the theorem be applied to them or not? I think this is where maybe the collaboration has to be between the two different sides of the communities to actually try to match the quantum foundations theory-independent way of thinking to the known theories and see actually, are we learning this thing? Are we learning something more than just the theory confirmation here?
Yeah, so maybe I would like to add something to that. So I think as far as the LO of the LOCC is concerned, it is very easy in any local theory because you're only interacting with local fields, okay? Of course, then that can propagate, but that is maximum C. So we know LO. I think the CC is for the CC, you always have to make extra assumption that the field is classical.
Right, but I don't...
LO is local operations. So when you have a system A, you do just local operations on it, is LO, and that is justified by the locality assumption of quantum field theory. In any quantum field theory, you can only do local operations on objects, right? I think the CC is, I find it, when I say it in talks, a bit more, I have to venture out to say that the field is everywhere classical, right?
Yeah. I actually disagree on this question of the locality, if I may, because this is part of it is exactly this. Like, I agree that in quantum field theory, obviously, we couple the Lagrangian locally with the points, but this is not exactly what the LO in LOCC theorem is, which is this coupling at the level of the unitary evolution.
Yeah.
And this seems...
No, not unitary, so any positive map. So the field which is around interacting with it can be traced out also.
Yeah.
So it is, but maybe we can discuss that. Yeah, if there is some gap here. But I think it is kind of, to me, it's kind of obvious that it should be a local positive map if it's a local theory.
No, I agree. But it's, I think it's not. This discussion is exactly what this is. It's not that clear.
Okay.
I can add a comment at this point. So I agree with what Andrea was trying to raise about the fact that we need really to understand what are we able to get more than what we already know. So of course, having a confirmation that gravity is a quantum phenomenon is going to be great. But there is this, to me, the most interesting aspect of this experiment would be the next step that could be really understanding the discreteness of the gravitational field, and in particular the discreteness of time. So in the last talk lightning talk by Pierre, this was mentioned. There is this beautiful work by Marius, by Pierre, and others. So let me give you a bit more of the context, because in quantum gravity, of course, we have these strong results about the discreteness of geometrical quantities like area and volume and so on. But indeed, the definition of discrete time is more controversial. And here it's worthy to clarify a thing, that when we talk about time, of course, we need to distinguish between measuring physical clocks. So in the moment in which we have a material clock, well, okay, at a fundamental level, I expect, if I take a very fundamental system, I expect this to have discrete properties. But on the other hand, what is interesting here is the fact that we are not measuring just the material clock. We can really measure an aspect of the gravitational field, namely an aspect of the metric, an aspect of the tetrads, depending on the definition that you want to have. And in this context, the next step, the next connection that I want to make is that measuring the discreteness of time in quantum gravity is strongly related to the presence of the cosmological constant. So we have this work, myself and Carlo, on the fact that if you want to have a discrete time in quantum gravity, this should come together with a maximal size of the universe, a compactness of the phase space that corresponds to the presence of a cosmological constant. So, and this connects also with what Eugenio says, that there is these beautiful connections between experiments in the lab and things that we can learn about cosmology, informations that we can import on the largest scale. So
okay. So actually, I was about to raise that point for discussion because no one commented on that. So maybe I have a question on that. People can answer that. How compulsory is it to have discretized versions of time, as you say, maybe is not, but even the other things which I understand in loop quantum gravity, like area is quantized in units and things. So so if we go a bit more general, like we say that suppose there is some theory of quantum gravity, I mean, how generic should we expect for things to be quantized in units of say h bar, units of action, if we in literally any kind of theory of quantum gravity?
I think there was a comment before during the discussion regarding how well defined are the operators that correspond to these quantities, and I think that there is a problem of perspective. That I mean, if you start from the idea that you have to start by classical general relativity and go down, of course, you may encounter a number of questions about a proper mathematical definition of things. But what we want to do in quantum gravity is vice versa, believing strongly what the quantum theory is telling us about its structures. So what we do in loop quantum gravity is really starting from a gauge theory where the fundamental gauge group is the Lorentz group, and there is a fundamental discreteness there in the fact that once you gauge fix, you have the group of rotations. So like for the angular momentum, the presence of the discreteness is really something that comes out from the fundamental symmetries of the theory, starting in a full quantum manner, and then recovering the continuous theory as and recovering the classical limit. So well, people may have a different opinion, but I would say that people that comes from loop quantum gravity, I mean, the idea is that there is a fundamental level, a quantum structure of reality, and in this structure of reality, there should be a quantum discrete spectrum.
Right. Okay. Thank you. Yeah, Carlo, wanted to say something. Yeah.
Yeah, I would say that the existence of discreteness seems to be a core aspect of at least some approaches to quantum gravity, like loop quantum gravity. What is far clear to me, and I think it must be much better studied, is how one goes from this expectation to the idea that what Pierre was talking about, that the difference of proper time in the interference count as a fundamental time. I think that has so far been done very hand-wavy. So let's imagine that that's different proper time is really correspond to an operator that has discrete spectrum in the fundamental theory, and that's that's to be filled, I would say.
Okay. Right. So you made a comment towards the end. So, Francesca, you were saying that the size of the universe was relevant to this. So is it like the infrared limit? Okay. So that discreteness is really because you do not have an infinite line, like you have a finite time of the universes. Okay. But the discreteness of these areas are coming from something more fundamental. Like,
yeah, that's much more clear. Okay. That's much, and I think the questions that I forgot your name, Carlos, from Mexico, was raising. This were much debated 10 years ago. In my opinion, they're solved. I mean, this is not a moment of reopening this. In my opinion, these are clear. Within the theory, once again, I mean,
right.
Carlo, just
question
a follow-up on this, because there is of course the discreteness of the area, but the area there is an object that is well defined is also the area of a Lorentzian area in which you have the two components. So the expectation, in my opinion, should be that this should be discrete too. But again, this comes. There is Wolfgang here who worked a bit on that. But to me, then the point is that if you want to go the way having also the Lorentzian area to be discrete, you should have cosmological constant and different mathematical structure on the base there.
Okay. So I think we will soon end the session. So I had just one question regarding also. So again, I did not fully understand the talk probably. So there was a comment that the state of gravity and the source was an entangled state when you took these longitudinal modes into account, right? And of course, as you know, people also say that you do not write an entangled state because the mass itself is the curvature. So you do not separately write it as a Hilbert space. If you want to write an entangled state, then you have to introduce a Hilbert space for the longitudinal modes, right? So I don't know whether I'm misunderstanding. Is that what is being done? Because then there is some kind of mismatch with people saying that the mass itself is the source of the curvature. You do not write there's not an independent Hilbert space. And then also in our virtual graviton picture, that is also fine because the vacuum is the vacuum of all the fields, but anyway, it's always vacuum. So we do not have a. Yeah, Carlo, you wanted to comment on it?
There's a Hilbert space for the source, and there's a Hilbert space for the field,
right?
And the split between the two parts, it's not defined a priori independently of the sources,
right?
So there's a Hilbert space for the field, and if you do a split and then add the source, you do something wrong. So the two Hilbert spaces, and when the source is split, the space is entangled. The minimal energy state, not any state, of course.
Right.
In fact, at the beginning, the source is split and it's not entangled. That's the point. It gets entangled dynamically, slowly.
Okay. Maybe I have to understand this.
Yeah,
better.
we can.
Yeah,
Can I ask a question? Whether to see what people would agree about the main discussion. The gravitational entangled experiments, what came out of the discussion is that two ways of thinking about experiment, or two classes of experiment. Experiment like measuring the Higgs, which are confirmation or disconfirmation of theories, and then theory-independent experiments. So as confirmation or disconfirmation of the theory, they're super interesting. As theory-independent statement, I haven't understood exactly what they are. They do not tell us anything interesting, or they might tell us something interesting is this LOCC details could be filled up? Is that the question?
Yeah, I don't. I mean, to me, CC is an assumption. You're restricting, right? Naturally, there is always quantum communications because, but we restrict with decoherence. We can justify classical communication. But LO to me is like, how did LO arise in the first place? Why do we see we can do operations on Alice and we do not need to do Bobby? It arose from nature. Like it's from quantum field theory to start with, right? It is. I mean, of course, there can be a signal then for your action, but that will only go at the speed of light. So I think the LO is based on our experience that we can locally control systems and not, not disturb a separate system, because that is how that is coming from the locality of nature, right? Of course, as I was telling earlier, that I am going a bit from that to because there are these non-local models I'm aware of which are still Lorentz invariant by some weird, because they just use the box is Lorentz invariant, so I think of it more now in the sense of how a gauge field interacts with a source. So you still have this trilinear kind of interaction, right? Input, output, and some field. So that is probably the assumption here. So then, even if the things are overlapping, that is still LO, because it's only this field can interact with this object, and they cannot interact with the other one. This is why I'm sometimes thinking whether this is it the locality we are using so much, or is it more the locality of this the form of interactions, which are always psi bar psi phi kind of thing.
I think with this comment could be the perfect closure.
Okay. We have to have lunch as well. Yeah.
Yeah.
Okay, thanks for all your contributions.
Thank you, Sougato. Thank you so much for sharing and for your insights. And food is ready.